There are times when the night sky does more than simply shimmer. It seems to whisper that a larger order is at work, hidden behind the veil of apparent randomness. The last week of September 2025 delivered exactly that kind of whisper, one so layered that scientists, skeptics, and dreamers alike found themselves questioning the familiar guardrails of cause and effect. On September 24th, an otherwise quiet period for stellar monitoring was shattered when astronomers detected the sudden brightening of Nova V1193 Centauri, a white dwarf that had been quietly siphoning gas from its companion star until runaway fusion ripped across its surface. Its brightness spike was followed less than 48 hours later by another outburst, this time from Nova V809 for Saturn, producing a double flash of high-energy photons pouring toward the inner solar system. These explosions were not the brightest novas ever recorded, but their nearly simultaneous eruptions injected our neighborhood with a flood of gamma rays and X-rays energies that can ionize matter across unfathomable distances. If the novas had been isolated events, they might have passed as just another line in the endless catalogue of cosmic violence. But the timing set the stage for something stranger. Within days, Comet Swan 6-2022, a fairly unremarkable comet that had already survived its closest approach to the Sun, earlier in September, suddenly blazed in intensity. Its brightness jumped nearly a full magnitude in just hours, while its tail extended across the sky like a banner unfurling in response to some invisible conductor. Astronomers in Chile and Australia reported that Swan's coma was not only larger, but electrically livelier. Spectral lines suggested fresh carbon monoxide and carbon dioxide outgassing, a sign that deeper layers of volatile material were being exposed. This would have been remarkable enough, yet the cosmos added one more strike to the sequence. On September 29th, the Sun itself flared violently, releasing an M-class eruption that hurled a massive coronal mass ejection, CME, directly into the region of space Swan was crossing. The coincidence was staggering. 2 novas, 1 cometary outburst, and a solar explosion all within less than a week. Mainstream astrophysics urges caution here. Statistically, random clusters of rare events will sometimes occur close together. The human mind evolved to detect predators lurking in patterns of rustling grass, cannot help but string such events into narratives of hidden design. But every so often, the coincidences cut so sharply against probability that even cautious researchers feel the tug of deeper questions. What connects a nova thousands of light years away with a modest comet less than a quarter of an astronomical unit from Earth? Could Swan's outburst have been primed by the incoming radiation from those distant stellar detonations? Or did the comet's timing merely trick us into perceiving synchronicity where none existed? The idea that a flood of high-energy photons could destabilize volatile pockets in cometary nuclei is not entirely implausible. While the energy flux at Earth's orbit from a distant nova is minuscule compared to sunlight, the penetrating power of gamma rays allows them to reach subsurface reservoirs of ice shielded from ordinary solar heating. If such radiation hits Swan at precisely the moment when stresses inside its nucleus were already near breaking, it could have triggered the release that made the comet suddenly bloom in brilliance. And yet, the sequence did not stop with Swan. The CME on September 29th seemed almost choreographed. Its direction aligned eerily close to Swan's trajectory. Observers recalled the famous 2007 CME that sliced through Comet ENC's tail, severing it in full view of NASA's stereo spacecraft. Such tail disconnection events are well documented, Magnetic reconnection between the solar wind and a comet's plasma envelope can literally cut a comet's luminous tail away, leaving it to regrow within days. But the deeper mystery lies in the timing. Swan's outburst erupted on the 26th. Exactly 3 days later, the sun flared. Some researchers quietly asked, could the mass of plasma Swan injected into the solar wind have propagated upstream, subtly altering the magnetic environment of the corona and nudging an unstable region toward eruption? The consensus answer remains no. The sun's energy dwarfs that of any comet by orders of magnitude. But in nonlinear systems, small triggers applied at just the right threshold can unleash avalanches disproportionate to their size. Hovering behind these unfolding dramas is another player, still invisible from Earth because of its low elongation near the Sun, 3I Atlas, the third known interstellar object to enter our solar system. Unlike its predecessors, Oumuamua and 2I Borisov, this newcomer is on a trajectory that will bring it close to Mars in early October before sweeping to perihelion. On October 30th, early modeling suggests it may carry a significant load of If true, Atlas could blossom into a far more spectacular visitor than Borisov ever was. A genuine interstellar comet flaring into activity under solar heating. Thus, the stage is set. A double nova injection of radiation, a comet's unexpected awakening, a solar flare aligned with uncanny timing, and an interstellar wanderer racing toward the inner solar system. If this were a symphony, the opening chords have already been struck, and the crescendo builds toward October 21st, the date when Swan makes its closest approach to Earth. The moon hides in new phase darkness, and Atlas hovers just weeks from its most active point. Are we watching choreography, as though some hidden order arranges these events? Or is it simply chaos, with human minds weaving threads of connection where none exist? The only way forward is through observation, data, and relentless skepticism balanced with curiosity. For now, all that can be said is this. In less than a week, the cosmos delivered a cascade of signals that demand our attention. And as the calendar turns toward October, the unanswered question grows louder. What exactly are we about to witness when multiple streams of electromagnetic energy, plasma, and interstellar debris converge in the heart of our solar system? The comet had been predictable, almost disappointingly so. For weeks after its September 12th, perihelion Comet Swan followed a gentle light curve, brightening and fading in rhythm with expectations derived from centuries of cometary observations. Amateur astronomers recorded its coma, modest in size, its tail little more than a faint smear requiring binoculars to appreciate. And then, with no warning, it exploded into brilliance. On September 26th, skywatchers in the southern hemisphere noticed Swan's coma had flared to nearly twice its previous brightness. Its magnitude leapt from 6.5 to around 5.7, barely within naked eye range, but dramatic enough to light up astronomy forums across the globe. Just as striking was its tail. What had been a dim, pencil-thin extension now stretched across 2.5 degrees of sky 5 times the diameter of the full moon. 2 observers in South America, South Africa, and Australia, it looked like a sudden cosmic banner unfurled above the horizon. The explanation, in broad strokes, is straightforward. Comets are unstable by nature. Their nuclei are regular conglomerates of dust, rock, and ices carry pockets of frozen gases trapped since the birth of the solar system. When solar heating penetrates these reservoirs, Volatile materials such as carbon monoxide and nitrogen vaporize explosively, producing sudden surges of gas and dust. The outburst of September 26th fit that pattern. Fresh material vented into space, scattering sunlight and enhancing the comet's visibility. Yet the deeper details reveal something stranger. Swan's orbital path kept it embedded within the heliospheric current sheet, the vast undulating boundary where the sun's magnetic field reverses polarity. Plasma physicists often describe it as a ballerina's skirt rippling outward at nearly 2 million miles per hour. Any object within this environment is subjected to shifting magnetic boundaries, fluctuating particle densities, and shock fronts that can dramatically alter its electrical state. And comets, far from being passive snowballs, are surprisingly powerful plasma generators. Solar ultraviolet radiation ionizes the gases streaming from their nuclei, producing swarms of charged particles. These ions couple with the solar wind's embedded magnetic fields, creating immense tails that act as conductive channels stretching millions of miles. Swan, after its outburst, wasn't merely brighter. It had transformed into an electrically active node embedded in the sun's sprawling plasma web. Dust adds another layer of complexity. Unlike planetary magnetospheres, which produce relatively clean plasmas, cometary environments are filled with microscopic grains of rock and organic compounds. When charged, these grains generate what physicists call dusty plasma, fourth state of matter whose behavior often defies the assumptions of magnetohydrosis. Dusty plasmas can self-against into spirals, generate electric fields, and produce non-linear responses to even small perturbations. In Swan's case, this meant that its tail and coma were not just passive clouds of gas, but dynamic electrical structures capable of influencing their surroundings. The photographic record tells the story. Before the outburst, Swan's ion tail was faint, diffuse, and poorly structured. Afterward, images showed a sharply defined streamer, its angle shifting subtly as if responding to new plasma flows. Dust lanes became more pronounced. The comet was not only venting material but reorganizing its electromagnetic presence. To plasma scientists, this was evidence of a system in flux, a body whose electrical interactions with the solar wind were entering a new, more volatile phase. But the timing raises questions difficult to dismiss. Two nova explosions had just flooded the inner solar system with high-energy radiation. Then Swan erupted. Days later, the sun flared. Were these connections real or imagined? Traditional astrophysics emphasizes scale. The flux of energy from distant novas is negligible compared to the sun's daily output. But comets, fragile and chemically diverse, might be more sensitive than planets or moons. Gamma rays and X-rays, unlike visible light, can penetrate deeply into solid matter, potentially destabilizing subsurface reservoirs of hyper. A tiny push imperceptible on planetary scales could be sufficient to crack open fresh seams of frozen gas in a cometary nucleus. If this happened, Swan's outburst might not have been entirely random. It could have been the visible consequence of invisible stellar explosions light-years away. And if Swan's sudden injection of plasma into the heliospheric current sheet altered the local electromagnetic balance, could it have rippled upstream, affecting solar regions already near instability? Here, the conversation enters speculative territory. Mainstream solar physics insists that comets cannot meaningfully influence solar activity. The Sun, after all, contains 99.86% of the solar system's mass and dominates its energy budget by dozens of orders of magnitude. Yet plasma physics has a way of humbling intuition. Small, localized changes can sometimes cascade into outsized effects, as in the case of auroras triggered by modest geomagnetic shifts. As September turned to October, the key question was not whether Swan's outburst was unusual. Such events are common in cometary behavior, but whether its timing was coincidental or symptomatic of a larger pattern. For observers on Earth, the next milestone loomed, October 21st, when Swan would pass just 10 million miles from Earth under the dark skies of a new moon. That night, the comet would be perfectly placed for observation, a living plasma experiment against the backdrop of stars. And Swan was not the only player. Hidden by solar glare, 3I ATL-AS continued its silent approach, preparing to loop behind the Sun and emerge near perihelion by the end of October. If Swan was the visible signal, ATLAS was the unseen mystery, an interstellar body whose chemistry, size, and behavior remained largely unknown. The prospect of both objects sharing the same turbulent electromagnetic environment within weeks of each other felt almost staged. Were we witnessing nothing more than coincidence? Or had the cosmos arranged an experiment, lining up Nova's comets and solar storms to test the limits of our understanding of plasma, resonance, and feedback in the solar system? As October advanced, anticipation built. Observatories scrambled to allocate telescope time. Amateur astronomers prepared their cameras. Space agencies quietly adjusted spacecraft instruments to maximize data collection. The sense was unmistakable. The universe had issued an invitation. Whether it would reveal choreography or chaos, no one yet knew. By September's final days, tension in the solar atmosphere had been building like pressure in an unseen fault line. Active region 4321, a magnetic, not rotating across the eastern limb, showed signs of stress loops, twisting, X-ray flux rising, filaments trembling at the edge of eruption. Astronomers monitoring with the Solar Dynamics Observatory warned of moderate flare potential. Few expected the region to produce anything exceptional so quickly. And then, with exquisite precision, the Sun erupted. On September 29th, 8:47 UTC, instruments recorded an M7 class flare, releasing in 10 minutes more energy than humanity has ever produced in its history. High-frequency radio signals across the sunlit side of Earth dropped into static as the ionosphere was pummeled with X-rays. The flare was accompanied by something more ominous. A coronal mass ejection, CME, a billion-ton bubble of magnetized plasma racing outward at nearly 2 million miles per hour. Here is where coincidence sharpened into something more haunting. The CME's projected trajectory aligned closely with the region of space Comet Swan was then occupying. Though not aimed at Earth, it appeared poised to intersect the comet within a matter of days. For comet watchers, this was thrilling news. They remembered 2007, when Comet ENC's tail was ripped apart by a similar eruption. Captured spectacularly by NASA's stereo spacecraft, Swan could be about to undergo the same fate. But the timing raised deeper questions. Swan had erupted on the 26th. The Sun fired on the 29th. That 3-day gap matches the time required for photons, plasma, and electromagnetic signals to traverse the distance between comet and star. Could the comet's massive outburst have altered conditions in the solar wind enough to nudge an already unstable region of the corona into eruption? Conventional wisdom says no. The Sun is too vast, too self-contained, to be influenced by the feeble plasma missions of a small comet. Yet history reminds us, nonlinear systems often ignore scale. A snowpack may sit stable for weeks until a single hiker's step triggers an avalanche. Could Swan's surge of ions, mass-loaded into the heliospheric current sheet, have provided the subtle disturbance needed to break the coronal balance? Computer models of CME propagation soon suggested the solar shock front would indeed sweep through Swan's neighborhood in early October. If the comet's tail disconnected, Earth-based telescopes might catch the drama live, a streamer of plasma torn away, drifting into space while Swan rebuilt its luminous appendage. Such an observation would not only confirm the physics of comet CME interactions, it would offer a natural experiment in how small-scale plasma structures respond to immense solar storms. Meanwhile, lurking in the sun's glare, 3I Atlas continued its approach. Its hyperbolic trajectory promised a close pass near Mars on October 3rd, just as the CME shockwave expanded into interplanetary space. If Swan's plasma tail would be tested, so too might Atlas's nascent coma. Early whispers from coronagraph data suggested the interstellar object was brightening faster than expected. Perhaps evidence of abundant volatiles never before exposed to solar heat. If true, Atlas could transform into a colossal plasma source, injecting its own disturbances into the heliospheric web at precisely the moment Swan and the Sun were locked in their interaction. The resemblance to a cosmic feedback loop became difficult to ignore. Novas pump high-energy photons into the inner solar system. Swan flares in brightness, releasing torrents of plasma. The Sun fires back, hurling acme aligned with Swan's orbit. Atlas drifts closer, preparing to unleash interstellar volatiles into the same turbulent region. Coincidence, perhaps, but even cautious scientists acknowledged the elegance of the sequence. If this is chance, one astronomer remarked privately, it is the most poetic chance I've ever seen. The key lay ahead. Would Swan's tail indeed suffer a disconnection event when the CME shock front arrived? Would Atlas brighten into visibility despite its solar glare? Would the Sun's activity escalate as both comets traversed the current sheet? As September gave way to October, the stage was set. The players: a nova-flooded sky, an outbursting comet, a restless star, and an interstellar wanderer were all in motion. The crescendo loomed, and the date circled on calendars around the world, October 21st, promised to deliver the climax of this improbable cosmic drama. If the universe were trying to stage a demonstration, it could hardly have chosen better choreography. October 21st, 2025, a date already marked by astronomers as the closest Earth approach of Comet Swan carried with it a cascade of alignments that seemed almost scripted. On that night, Swan would pass just 0.26 astronomical units from our planet, roughly 10 million miles. For a comet, this is close enough to blaze across the sky as one of the brightest objects of the season. Coinciding with this flyby, the Moon entered its new phase, eliminating the wash of lunar light and ensuring the darkest possible skies. It was as if nature had dimmed the theater lights for maximum effect. But the real intrigue lay elsewhere, in the regions of space our eyes could not reach. Hidden by solar glare, 3I Atlas pressed onward, approaching perihelion on October 30th. Its geometry placed it nearly on the same ecliptic plane as Swan, both objects threading their way through the undulating sheet of plasma and magnetic polarity known as the heliospheric current sheet. Rarely had two large, volatile-rich comets or comet-like bodies shared this turbulent zone simultaneously, much less during heightened solar activity. The heliospheric current sheet deserves emphasis. Imagine a cosmic skirt, billions of miles wide, spun outward by the Sun's 27-day rotation. Within its folds, magnetic fields reverse direction, plasma densities spike, and turbulence reigns. Any object embedded here, planet, asteroid, or comet, experiences fluctuating electromagnetic conditions that can reshape its plasma environment in unpredictable ways. For comets, whose vast ion tails act like antennas coupling directly into the solar wind, the effect can be profound. Now add a second layer, both Swan and ATLA, as generating enormous plasma envelopes at once. Could their combined output locally alter the heliospheric circuit, nudging currents that ripple back toward the sun? Plasma physicists hesitate, but analogies exist. Small perturbations in electrical grids can cascade into blackouts. Subtle changes in ocean currents can shift global weather patterns. Complex systems respond not only to magnitude, but to timing and resonance. And the timing of October 21st was exquisite. Swan at maximum brightness, Earth perfectly positioned for observation, the Moon invisible, Atlas nearing its solar peak. Meanwhile, the Sun itself simmered with tension, its active regions throwing off flares and CMEs at an accelerated pace as solar cycle 25 built toward a vigorous maximum. The possibility that cometary plasma and solar instability might meet in resonance was speculative, but the geometry begged the question. Observers prepared accordingly. Ground-based telescopes across the southern hemisphere were cued for Swan's display. The Parker Solar Probe and Solar Orbiter adjusted data collection modes to track CMEs and solar wind structures. Mars-based spacecraft, uniquely placed to observe Atlas as it approached perihelion, stood ready with spectrometers and dust detectors. Rarely had such a natural laboratory presented itself, with so many instruments poised to capture the unfolding drama from multiple vantage points. The practical implications mattered too. If Swan encountered the shock front of a Comet during its closest Earth approach, its tail could disconnect spectacularly visible to amateurs with backyard telescopes. If Atlas erupted into a hyperactive coma, its dust and gas might register as anomalous signals in solar wind data, perhaps even perturbing Mars's ionosphere. For scientists, these were not mere curiosities. They were tests of whether our models of solar-comet interaction were complete or in need of revision. But the larger narrative pulled at something deeper. Was this alignment mere coincidence? The inevitable byproduct of billions of objects tracing gravitational pathways through the solar system? Or was it hinting at a more tightly coupled reality? A solar system not of isolated orbits, but of interconnected plasma circuits. Either way, October 21st promised clarity. If the days passed uneventfully, with Swan showing only the ordinary effects of solar wind and Atlas remaining modest, skeptics would find their caution rewarded. But if flares erupted in synchrony, if comet tails twisted or snapped at precisely the wrong or right moment, then the conversation about electromagnetic coupling in the solar system would shift from fringe speculation toward mainstream consideration as Earth rotated into darkness. On the night of the 21st, humanity found itself with front-row seats. From mountaintop observatories to backyard cameras, from spacecraft orbiting Mars to satellites orbiting Earth, instruments strained to capture the moment. In the silence of the skies, the geometry had arranged itself. All that remained was to see whether the cosmos would play out as coincidence, choreography, or something stranger still. The universe rarely resolves its mysteries in neat packages. But the days following October 21st, 2025, offered data points that will occupy researchers for decades. For those who braved chilly pre-dawn skies, Comet Swan delivered on its promise. Bright enough to be seen without optical aid under dark conditions, It painted the heavens with a streamer that appeared to writhe from night to night. Amateur astronomers noticed subtle changes in its tail, kinks, bends, and sudden brightness drops that hinted at external forces at work. By October 23rd, telescopes captured what looked unmistakably like a tail disconnection event, a phenomenon where a coronal mass ejection severs the plasma tether between comet and sun. Swan had indeed been struck by the expanding shock front. Launched on September 29th, the spectacle confirmed decades of theory and echoed the famous Comet Inc. episode of 2007. But this time, under the watchful eyes of thousands of coordinated observers. Meanwhile, reports trickled in from Mars-orbiting spacecraft. 3-1 ATLAS, though still hidden in solar glare from Earth, began showing signs of outgassing more intense than anticipated. Spectral data hinted at the release of unusual volatiles, possibly exotic ices, unfamiliar in typical solar system comets. Its coma expanded rapidly, suggesting that this interstellar visitor was no inert rock but a chemically rich traveler, shedding its alien cargo into the heliosphere. Some instruments even registered fluctuations in the plasma environment near Mars, though interpretation remained cautious. Was Atlas altering its local space, or were the signals artifacts of normal solar turbulence? The Sun itself seemed unwilling to sit quietly. On October 20th, an M8 class flare erupted from a different active region, followed by 2 fast CMEs. By the 24th, a smaller but complex sequence of flares peppered the solar disk. None were Earth-directed enough to cause catastrophic geomagnetic storms, but auroras danced unusually far south, delighting watchers from Europe to Australia. To those steeped in the narrative of convergence, the timing was irresistible. 2 comets embedded in the heliospheric current sheet, both active while the Sun produced its most sustained sequence of flares in months, and yet the skeptic's case remains intact. Solar maximums are always noisy. Comets often outburst. Tail disconnections happen whenever CMEs and comets coincide. The raw probabilities of overlap increase dramatically when multiple observers search eagerly for patterns. Statistical caution demands humility. These events may still be nothing more than coincidence dressed in cosmic grandeur, but the alternative, possibility, glimmers tantalizingly. Could the chain truly exist? Nova radiation perturbing cometary volatiles. Cometary plasma mass-loading the solar wind. Subtle shifts propagating back toward the Sun. And solar flares cascading outward to reshape planetary environments. If real, it would mean our solar system functions not as a collection of isolated bodies, but as an interconnected plasma circuit, with information and energy flowing in loops we barely comprehend. The plasma bridge hypothesis, long relegated to fringe journals, suddenly feels less outlandish. Swan and Atlas may have acted as temporary electrodes in a vast electrical circuit, their outbursts amplifying disturbances that resonated through the heliospheric web. The evidence is not conclusive, but neither is it dismissible. The October window has given science exactly what it craves most: anomalies worth pursuing. For Earth, the practical impacts were modest. Radio operators reported shortwave blackouts during the flares. Airlines adjusted polar routes to avoid communication disruptions. Aurora enthusiasts were rewarded with luminous skies that seemed to ripple in sympathy with Swan's tail. Power grids, hardened since the mid-20th century, weathered the storms without major incident. The drama was therefore primarily observational cosmic ballet visible to telescopes and instruments. rather than a catastrophe felt by daily life. But the cultural resonance reached further. Headlines framed the alignment as the most unlikely cosmic coincidence in a century. Social media buzzed with images of Swan's fractured tail, stitched together from dozens of backyard astronomers across continents. Too many, it felt like the sky had briefly lifted its veil, hinting at hidden symmetries beyond ordinary experience. For scientists, the task ahead is clear. Analyze. Teams are now cross-comparing comet brightness curves with flare timings, running simulations of plasma feedback loops, and scouring nova archives for similar alignments. If patterns emerge, if outbursts repeatedly cluster around external triggers, then textbooks may require revision. If not, the October convergence will stand as one of the most beautiful demonstrations of chance in action. A reminder that random distributions sometimes mimic orchestration. Either way, humanity gained something priceless. We witnessed a moment when stars exploded, comets flared, the sun erupted, and an interstellar visitor threaded through it, all within the span of a single month. To live under such a sky is to feel the pulse of a universe alive with motion and mystery. As November dawns and Swan fades into distance, ATLAS continues its journey, growing brighter before swinging past the sun and out into the dark again. The sun rolls on in its cycle, promising more flares, more storms, more mysteries. And the novas that set the sequence in motion fade into background starlight, their energy already spent. So was it choreography or chaos? The verdict may never be absolute. But the October window proved something deeper. In the vast electromagnetic web of the solar system, even the smallest actus a fragile comet, a pulse of photons from a distant star can inspire us to reconsider how tightly woven the threads of reality might be. And perhaps that is the universe's real message, whether by design or by chance. It is our curiosity, our willingness to watch and wonder, that transforms coincidence into discovery. As our journey through this cosmic sequence comes to an end, one truth lingers above all: the sky is never silent. In just a few weeks, novas erupted light years away. A comet awoke with startling brilliance, the sun unleashed its fury, and an interstellar traveler slipped quietly into our solar stage. Was it all a coincidence, a random clustering of rare events, or are we glimpsing hints of a deeper order woven into the plasma threads that bind our universe? What makes this moment so powerful is not certainty, but mystery. Swan's fractured tail, ATLAS's secretive glow near the sun. The sun's restless storm's itch offers data we can measure, but together they suggest questions that transcend numbers. Could comets be more than relics, acting as conduits in a solar circuit? Do interstellar wanderers carry not just exotic chemistry, but messages from the galaxy beyond? We don't yet have the answers. But that's exactly why the next chapter matters. In the weeks ahead, as ATLAS approaches perihelion and solar cycle 25 climbs higher, the universe may reveal more than we expect. Stay with us, because this story isn't over. The curtain has only just risen.